So let's see whether we can deal with that Hopf bifurcation also with our multiple scale approach. That seems very natural because at the Hopf bifurcation, we have that the eigenvalue is a purely imaginary pair. So that means there's a finite frequency, meaning it's not zero, not small, but the growth rate is actually zero at the bifurcation point. And so we have clearly two different time scales. And we want to explicitly use that and see what equation do we get that way. Let's do that with the same model or same system of equations that we had before. So let's see, it was x dot equals minus x minus y plus 2y squared, and y dot equals 2x plus 1 plus mu y minus 4xy minus 4y squared. Okay, so multiple scales, always the question, how do we scale those quantities? So at this point, we don't really know. We don't know what the equations are. Let's recall. So our general strategy is that we should choose the scaling so that is consistent with the form of the equation that we expect to obtain for the amplitude on the center manifold. We don't know what that equation is going to be. So that's not too helpful at this point yet. So we'll see later that because of time translation symmetry, the oscillation amplitude is of the order of square root of mu. And so we choose the following scaling. We say mu is equal to epsilon squared mu2. We take a slow time scale, epsilon squared t, and we take the solution u, which I take to be x, y. U is order epsilon. Okay. So now we have not just a slow time, we actually have a fast time also. So we really have now a full-fledged multi-scale problem. So we have u is a function of fast time and slow time. So we really get that this becomes an explicit derivative with respect to the fast time plus epsilon squared with respect to the slow time. Okay, we can handle that. And now we need to write these equations here in a more constructive form. So what will happen? Well, first, these time derivatives will generate a fast time and a slow time. The fast time, the term with the fast time, will be not generate an additional order of epsilon, whereas the term with the slow time will generate an order epsilon squared term. So that means these time derivatives generate something that's just of the order of x and something that's on the order of x times epsilon squared. So, and then we expand everything, right? We expand u, meaning x and y. We expand u in epsilon as well, where u is of order epsilon, and then will be epsilon squared, epsilon cubed terms. We'll do that expansion, and we expect there will be some solvability condition emerge at some order, which we don't know yet what order that will be. And so we need to look out for singularities of the matrices or the operators that we have. Okay. But in general, whichever detail will come out eventually, it will be clear that we'll have a linear operator times at order epsilon times u1 equals something. At order epsilon squared, we will have the same linear operator times u2, which is the epsilon squared contribution for u, equals something else. And so we will have that at all orders. And so we'll always try to solve, invert the L0, which will not work because of singularity, and so on and so on. But let's therefore write it in that form that we have the L0 on the left-hand side and all the other stuff on the right-hand side, because all the equations will be of this inhomogeneous form. Okay, good. So let's get started. It's a little bit messy. We'll have, if I separate fast and slow times, I get on my left-hand side, I get 1 plus d by dt, and 1 minus 2 minus 1 plus d by dt, this thing acting on u is equal to minus, and now we have the slow time, d by d slow time u, plus, okay, so now we have that mu is of order epsilon squared, so that will show up on the right-hand side as an inhomogeneous term, and I'll call it an L2, because in principle there could be a term acting on y, on x, and also in the other equation. So there will be an L2, which depends on mu, and that will also act on u. And then there's a nonlinearity, which, well, let's write it out first. What's the nonlinearity? It's 2y squared minus 4xy minus 4y squared. And just to have a handle on it, let me call this here nonlinearity at second order of u and u. Okay, so that's our equation. And we'll expand now u. So u will be at order epsilon. Well, let's first write it out sort of in this form, so we have something to talk about with all the without the details. So it will be just u1, u2, u3 with different orders in epsilon, and all of these terms will depend on slow and fast times, right? So I'm not going to write that out in detail, but here are, as a reminder. Okay, so now at order epsilon, what do we get? Well, when we plug in, we'll get back the linear problem. And so therefore, the leading order term in order epsilon will be the eigenvector associated with the eigenvalue that, with the eigenvalues that cross the imaginary axis, which we call V1. And then amplitude, which we don't know yet, times e to the it, because the frequency is actually 1. I didn't say that here, but we have, actually in this case, in this example, we have this is plus minus I. So the frequency is 1. So we have this, and we can allow the slow time to appear in the amplitude. And we also have the other eigenvector, right? There's one eigenvector for the plus eigenvalue, then there's another eigenvector coming with the minus eigenvalue, which of course is the complex conjugate of the same thing. So we have V1 star times A star of t e to the minus it. So that's what we have at order epsilon. Order epsilon squared, what do we expect? Well, we have a nonlinear term here, which is quadratic. So that means if we square this u1, it will generate an e to the 2it, it will generate an e to the minus 2it, and it will generate an e to the it, e to the minus it, meaning a constant time-independent term. So therefore, we need to include in our terms at order epsilon squared, we need to allow for terms of that type. So that means I'm going to write down a u2 for second order, 0, standing for no fast time dependence. This will depend on slow time. Then there will be a u22, also depending on slow time, but with e to the 2it, right, from the squaring. And there will be an u2 minus 2, which will be e to the minus 2it. Okay, I know that everything has to be real when things are added up. So this term and this term have to add up to be something real. So u2 minus 2 must be the complex conjugate of u22. I might as well just say that right here. So I have here u22, but it's complex conjugate. So since I have done that problem before, I know we will have to go to order epsilon cubed. And so at order epsilon cubed, what will show up? Well, we don't have a cubic nonlinearity, right? It's just a quadratic nonlinearity. But once we have the terms at order epsilon squared, say the u2, 0, when you take the square, you have a u20 times an v1. That would generate the term e to the it. Similarly, u20 with e to the minus it will generate the term e to the minus it. And there will also, from here, will be an e to the it, and from here will e to the minus it. And then we'll also have e to the 3it, e to the minus 3it. So in short, the terms that show up at cubic order are either plus or minus 1 in frequency or plus or minus 3 in the frequency. Okay, so that means we can write that down. We can say there will be a u31 times e to the it, a u31 star, e to the minus it, plus u33, e to the 3it, plus u33 star, e to the minus 3it. And that's all we do until cubic nonlinearity. Okay, good. So what's going to happen? Well, we need to plug that in, and we expect a solvability condition to show up. Well, where does it come from? This is this linear operator. Let me call it L0. This is that linear operator that when you insert the expansion for u in the equation will show up at each order. At each order, we'll have this guy show up, and at order epsilon, it will multiply u1. At order epsilon squared, it will multiply u2, and at order epsilon cubed, it will multiply u3. So the question is this guy singular? Now, the only terms that we have, they're all some kind of Fourier modes with some frequency, 0, 1, 2, 3, essentially. And so it's worthwhile looking at this operator just applied to those frequencies. So let's do that. So if we have now, we apply L0 to some vector, should we call it something? Well, some vector u. No, that's confusing. Let's just call it w. We won't need it actually right now. Times e to the I n t. We just want to know what happens with the frequency n. And so what do we get? Let's do that. L0 times w e to the I n t is what? So I'm really what I want to do is I want to transform this operator where there's the derivatives in there. I want to convert that into a simple matrix. So I only want to apply the time derivative, which for my exponential will simply bring down an in. And so this thing here will be transformed into a matrix 1 plus in, 1 minus 2 minus 1 plus in. Okay, so let's write that down. It's the matrix 1 plus in, 1 minus 2 minus 1 plus in times w. Okay. So we want to know whether this guy is singular. For which ends is it singular? Well, we need to calculate the determinant. Oh, I should call this something so I can talk about it. So this is, I'm going to call this L0 of n. And so if I calculate the determinant of L0 of n, what is that? That's simply minus 1 plus in times 1 minus in plus 2, which is minus 1 plus n squared plus 2, which is non-zero except when n is equal to plus or minus 1. So singular is only L0 of plus minus 1 and not singular all the others. Okay, good. So then we are in business. We can now essentially proceed and plug in. Maybe while we're at it, we know that, okay, so what will happen? We plug in order epsilon, epsilon squared, epsilon cubed. And at each order, we check whether we have a singular operator on the left-hand side. We now know what we need to look for. We need to look for n, that frequency. And then, if the operator is singular, then we get from the Fredholm alternative theorem, we get a solvability condition, which tells us that the right-hand side of the equation times the left zero eigenvector of that operator must vanish. So we should calculate that left zero eigenvector. That is straightforward. Let's just do it. So we need to know what's the vector. Let's call it x plus y plus. We need to have this of +1. When is that 0? That's x plus y plus times 1 plus in 1 minus 2 minus 1, not in, this is 1, right? Minus 1 plus I, and that's supposed to be 0. And this implies that we have x plus times 1 plus I minus 2 y plus is equal to 0. So that gives us y plus as a function of x plus. There's also the left zero eigenvector for when we have -1 here, which just changes the sign here. So let me not write that out, but it's straightforward to get the other guy. Okay, so we're ready. And now it's now a bunch of algebra. In principle, we have the structure down, and so we just have to apply it well enough. Okay, so let's go. Order epsilon. What do we have? Let's go back. Unfortunately, we have to scroll a lot. So at order epsilon, L0 is order 1. So we just get a U1. And the right-hand side is U1 is order epsilon. This is actually order epsilon cubed. This is order epsilon cubed. And this is order epsilon squared at leading order. So we see at leading order, at order epsilon, we simply have L0 times U equals 0. So we have here L0 of U1 is equal to 0. But that's just the linear stability analysis. That's just how we determined these vectors in the first place. So that's just recovering. Oh, that's not what I wanted. Sorry. I wanted to have this. That's just going to recover this. That always is the case, right? So in some sense, it's just sort of a double check that we are not doing something really stupid. Okay, then order epsilon squared. So there we have L0 times U2 is equal, and on the right-hand side we have, well, as I noted, these guys are order epsilon cubed, so you only have this guy. So we have now N2 of U1 and U1. That's going to be a quadratic term. So this is N2 of U1 and U1. So what does that mean? I guess we have to write it out so we see what's going to happen. At least once we should do it. So the x component is 2y squared. 2y squared, we need that of the U1. The U1 is like a V1 times e to the IT. And so that's the y component of V1 times e to the IT. And when we square that, we get either e to the IT squared in this term, or we get e to the minus IT squared, or we get the mixed product. Okay, so how do we want to write that out? Well, maybe I should write it once. So this is a times v1 e to the it plus a star v1 star e to the minus it comma a v1 e to the it plus a star v1 star e to the minus it. And now we have to take the square of the y component and in the x row and in the y row something else. It's going to be a little bit algebra, which I'm not going to do now. It's not too instructive, except that we recognize again, as we predicted, that we will have a term e to the it times e to the it, which will be e to the 2it. We will have a term e to the it times e to the minus it, which will be a constant, and then e to the minus 2it. And so let me just write down what you get when you now collect here, you collect in this big thing, you collect the different frequencies. So there will be an e to the I 0t. And when you do that, out comes that x20, y20 is going to be 0 for a times a star. Remember x20, y20, those are the components of u20, where we had predicted that we will need a term that has no frequency or zero frequency. Okay, and if you go for e to the 2it, then the answer is, after a little algebra, is x22, y22 is equal to minus 2i, 2 minus 1 plus I times a squared. So the only reason I wrote that down is because it tells us what's always happening. But so you see there's a term a times a star, which I completely expected there. Why did I expect that? Because the way we expand this whole thing is that we say the leading order, there's an e to the it term, which I multiply with a, whereas the e to the minus it term is multiplied with a star. So that means whenever I have an e to the it, there's an a with it. Or the other way around, an a represents actually a term e to the it. So that means if we're here down here, we're looking at terms that have frequency 0. That means it has to be an e to the it times e to the minus it. So it has to be a term a star. Analogously, if you have e to the 2it, it has to be a term a squared. If that's not the case, then something went wrong, right? So that's why I wanted to write this down explicitly. Okay, and then we go to cubic order, which, as you anticipate, will be worse, so to speak. So what do we get there? Well, we again get our L0 of U3, and then we get what we have on the right-hand side. We have slow time U, L2U, and then an N2. Okay, so we have, let's write that down. We have minus a slow time derivative of U1 plus L2 also on U1. And then we have plus N2. So that's a quadratic nonlinearity, and it needs to contribute to cubic order so that it can do that in two ways. It can have a U1 and a U2, or it can have a U2 and a U1 in its two arguments. Okay. So now we know at cubic order, here we have already an e to the it term showing up, another e to the it term showing up. And then when you have here in this quadratic nonlinearity, remember that in the x component, the quadratic nonlinearity is simply y squared, meaning this times this. And so we square it. So U1 has a frequency 1, U2 has a frequency of 2 and a frequency of 0. And so therefore we can combine these two terms when we multiply them. They will generate frequencies 1 in different ways. either from the U1 together with the U2 0, right? That's what we have here. Or the U1 with the -1 frequency, the complex conjugate, together with the U2 2, which is from here. So there are two different ways that each of these will contribute to the e to the it terms, which are lead to the singular terms, to the secular terms. So therefore, we have now to satisfy a solvability condition, and we have that by we multiply with our left zero eigenvector. So we multiply with our guy v plus that we've calculated, and so we get, when we do that, v plus times L0 will be 0, so the left-hand side will be gone, and so we simply have v plus times this, and so on, has to add up to 0. So we get, therefore, the equation, when everything is said and done, well, not everything, when to this point, v plus times d by dt u1 equals v plus times L2 u1 plus n2 u1 u2 plus n2 u2 u1. And now you just have to plug in. I mean, this bunch of algebra, which is unpleasant, and so there's a bunch, some steps are missing now. I'm going to skip some steps, but I'll give you the answer, because the answer is really important now. So when everything is said and done, we actually get this equation. We get an equation for that complex amplitude, A, and it has this form. Let me box it. This is a fine equation in the sense that, as it should be, when mu is 0, meaning when mu2 is 0, the linear term vanishes. Wait a minute, should it vanish? It has a frequency, right? It's a Hopf bifurcation. So it didn't vanish in a center manifold calculation. There it had like an I. Well, the point is A is the amplitude of the term oscillating with the frequency 1, right? Here. So the frequency 1 is already taken out. So therefore, at the Hopf bifurcation, the amplitude A is not oscillating any further. It just has, so therefore this eigenvalue is 0, because we factored out the e to the it already. Okay, then as we change mu, we have a real part that's positive, so the amplitude will grow, and the frequency changes with mu. We had that also in the center manifold calculation. Good. But you probably noticed already that in that center manifold calculation, we had a whole slew of terms. We had an a squared, we had an a star times a. I forget what else we had. But the point is, we had quadratic nonlinearities and no cubic nonlinearities. Here, we have a cubic nonlinearity, only one, and no quadratic nonlinearity. That is weird. This doesn't look right. This doesn't look as if these two equations describe the same system. Now that's disconcerting, or maybe I shouldn't make it that drastic. Dramatic. It would be disconcerting if it was really true the way I said it. It turns out, and that's our next step that we need to do, that the two equations do describe the same phenomenon in different ways, and it turns out that the multiple scale ansatz or approach makes a special choice, so to speak, for the equation, and it comes up with this normal form, whereas in the center manifold calculation, you don't get to that normal form, whatever normal form means. Well, we talked about normal forms before, at least in terms of words. We had, like, for the saddle-node bifurcation, normal form, I told you, was mu plus x squared and stuff like that, but we didn't really talk about what normal form means. So we have to get to that, and we will find out that the center manifold equation that we have can be transformed into this equation in a way that uses certain transformations that we'll do next time. Okay, but at this point, what you want to take from it is that the multiple scale approach works in principle, straightforwardly. You just have to separate the different frequencies, but otherwise it works just like you had done it for the steady bifurcation. It generates a solvability condition at order epsilon cubed, which we also want to understand why that is the case. And we'll find out that it's consistent with the multiple, with the Zinner manifold approach. Okay.